very introductory preamble. Indeed, this talk is targeted to physicists. So my idea, my intention is not to give for granted anything on the machine learning side. Okay, but please stop if I'm saying something which sounds obscure or not understandable. After this very short introduction, which allows me just to give some, to define some object that I will use later, I will enter into, let's say, 3 separate blocks. And if times allow, I will cover all of them. If it does not, it doesn't matter. I can organize the material on the fly and conclude also in the middle. I prefer rather to convey some clear method that obtain full covering. So please stop me also if you feel like. So the first block I was saying is an attempt to find, let's say, a corner, a deep learning model and a model in physics, in which to speak about the connection between these two words in a somewhat precise way, at least formally. We will see that this is possible, but nevertheless, there are important differences. Then, in the second block, I will comment on an interesting observation. Let's say the physicists take on a very popular architecture, which is convolutional neural networks. In the end, in the third block, I will descend into something a little bit more technical, related to what I'm doing as a research activity. And it is related to regularization with methods that are inspired by statistical mechanics. In particular, you can recognize that I will use entropic functions. At the end, I will conclude. So, as I was mentioning, a general disclaimer that I feel like to make is that I will be introductory and not very technical in general. Sometimes this is because of lack of knowledge. Some others, well, it is simply for the sake of the presentation. So if you are interested to some aspects that I touch, you can ask either now or later. I might be able to provide more details. Okay, so moving on to the preamble. At first, speaking to physicists, probably the most important advice if you want to approach machine learning is to remind yourself of your laboratory course, and more, especially if you then worked in theory, in theoretical physics. Of course, if you are an experimentalist, probably you have cultivated that kind of expertise far more. Because it is true, to some extent, that machine learning can be at least thought as a sophisticated, a complicated version of things that we saw in the lab courses. For example, 2 very typical and paradigmatic tasks are that of regression, so finding the best fit to a set of data points, can be interpreted as minimizing a cost function. In that case, the cost function will be an error, for example, a square error, but can be more general. And another class of problem is that of classification. You can think of that as having data points, experimental data points in a big space, and you want to divide them in clusters with some characteristics, and you are looking for a surface, a parametric surface, which is able to separate different families. Okay. In all cases, you can recognize that there are there is an ansatz in general. In this case for a function, in this case for a surface, with parameters. And the purpose is to find the best configuration, the best set of these parameters to the purpose, to minimize the cost generally. So we are in the realm of optimization. To give a definition of machine learning, I will use it as a synonym of artificial intelligence, meaning that we are dealing with machine learning whenever in dealing with a task, in addressing a task, we don't code with the computer, of course. We don't code directly an algorithm to solve the task. Rather, we code a meta algorithm that will find an algorithm that solves the task. Okay. So if you want a biological smile, we are doing what evolution does. Okay, to some extent, we are at an upper level. The most basic concept in neural networks is, not surprisingly, the artificial neuron. And it is fair to say that both at the microscopic level of the single neuron and at the level of the architecture, neural networks borrow and have borrowed a lot from biology. And well, I try to convince you of this by describing how a typical artificial neuron works. The artificial neuron is a device that has a set of input channels. Here are denoted with X, and a single output channel denoted with Y. What it does is taking the input channel, weighting them with coefficients that are called it is sensitive. Okay, that are maybe. Should I use this?
The point, yeah. I think otherwise.
Okay. Weights that are coefficients that are the parameters that we want to optimize. We are doing a linear combination, and here there is another parameter which is an offset. It's called bias. This linear combination is fed into a transfer function, which is sigma, and the transfer function can have a shape of this kind. Okay, this is a rather generic family of functions. You see that if the argument that we fed, the linear combination of the inputs, is very low, we have zero response. If the same argument passes more or less these threshold values, the neuron starts to respond and starts to fire. So in this firing comment, probably you recognize something of the biological neuron. But as I was saying, of course, we are interested in neurons to make complicated architectures, to organize them in networks. And also the shape of these networks has received great impulse from the observations in the visual cortex of cats, for example.
Daniele,
yes?
a question. So why don't you use a step function? Or
right.
What's the dependence on the particular function you choose?
Yeah. The first question is easy to answer. Usually is because we want to train this network, and we need a gradient to be well defined.
Mm-hmm.
The typical choice is some smoothened version of a step function. Let's say. There are other choices, but okay, that could be regarded as a typical choice. The second question is difficult. Usually is something that you understand experimentally. So you try different functions and you try to understand what is the eventual effect at the level of the network. Yeah, yes, I'm supposing that we are interested in the behavior of a system of neurons, not of the single neuron. So we want to organize them in networks, and in particular, we are interested in hierarchical architectures. So we want to pile the neuron up, let's say, in a stack. And usually, well, and indeed, the term deep of deep learning refers to the depth, and the depth is this direction, this vertical direction in the here. So a deep neural network will have a lot of layers stacked one upon the other. And as you can imagine, we are interested in connecting the neurons that lay below with the neurons that stay which stay above. And so, referring to the function that we described in the previous slide, you see that we are composing neurons in the sense that we are composing their transfer function. So let's say that to gain insight on what the depth means, you can think that we are increasing some compositional complexity. So we have some combinatorial complexity. And in the sense that the first layer computes essentially a weighted average of the inputs. The second layer will compute a weighted average of a weighted average, and so on. Okay. Okay, so this was, let's say, less than a crash course in deep learning, but it allowed me to introduce some basic concepts that I will use later. So if you have questions, make that now, and otherwise I enter the first block. Okay, so the first block is an attempt to relate in some precise sense deep learning and renormalization. But at first, let's work at the level of the analogy. I guess what probably is everyone here already has some sort of feeling that the two things can be related.
Yeah, sorry, I don't understand, because the picture you made in which the trees converge,
yes,
is not the only possible one. I mean,
no.
Equal number of nodes at each level.
Yeah, or even the opposite. You can even have,
Yeah,
let's say, a higher number of neurons in a hidden layer than. And let's say that we are restraining to a set of graphs where there is a sense of layers. There are no connection between neurons on the same layer. There is, let's say, a structure that is well defined.
What I mean is that this picture seems to be biased towards renormalization in some sense. But it's not the only.
No, right. No, okay, this is an important point, and I will comment on that in a couple of slides. But yes, I agree. I agree with the comment. So, as an application, we can think to neural network as complicated ansatz. And so, since we usually deal with complicated systems like many-body physics, we can hope that using a sufficiently complicated ansatz, we can learn somehow the dynamics of the system and be able to make predictions. So, let's say this is a way which is very interesting from an application point of view. It might be less so from a theoretical point of view, because suppose that you have a very good and efficient network that is able to learn and predict a system which is complicated. Nevertheless, making good prediction in this case is not necessarily translated into a human understanding. Maybe you have a network that learned the problem, but you didn't. You are just an observer of something working, which is generally not the purpose, not for the sake of this talk. A comment which is that I will tirelessly underline is that in both cases there is a crucial role of the symmetries. I guess that on the physical side, I don't have to convince anyone here, but it is true also in machine learning that symmetries, and we will see, and symmetries are very important. There is also a very interesting line which studies covariant neural networks that try to push at the maximum this idea. Another important concept is that of locality, and it is easy to imagine that locality, if true, let's say, is a strong simplifying concept as well as symmetry, because think, for example, to the evolution of a system. If you can say that the evolution is governed by a local Hamiltonian, you are already excluding a big bunch of possibilities in its evolution. And more at a technical level, in both fields, we deal with variational ansatzes. And as a general comment, which applies to both sides, is that we have some complicated system with some complicated microscopic dynamics, and we want to have a compressed, a synthetic account. So we want to some extent to forget details and remain with an effective treatment of the system or of the task. So at the level of the analogy, let's say, it's easy to connect the two things. But now let's try, more or less following the line of Javier's question, let's try to make the connection more precise, at least in a specific case. So let's consider the variational renormalization group a la Kavanaugh. So here renormalization is meant in the sense of statistical mechanics. And we have a system of visible spins. Here, I have to learn to use this pointer. And Okay, which is described by a probability distribution. Okay, here I've been careless of the normalization. And the probability distribution is described in terms of an energy function, and so we have a Boltzmann weight start. The Hamiltonian, the energy function, can be quite generic. For example, can have this shape with different couplings, and we want to implement a coarse graining procedure, meaning that we want to define another Hamiltonian as a function of some auxiliary variables and grasp, let's say, the physical content of the original dynamics or the original probability distribution. So we introduce new variables, which are auxiliary, which are the hidden spin H, and we also introduce couplings between the visible and the hidden spin. So we are enlarging the system. The couplings are globally denoted with lambda. These are the parameters that we want to tune in order to make the renormalization step. So we have a larger system. We trace over the original, the visible spins, and we define a coarse-grained Hamiltonian. Let's say that here we are using the terms coarse-grained because we are already biased towards a typical idea in statistical mechanics and in physics in general, but it holds the comment that Javier was making, that here we can even consider cases in which there are more hidden spin than visible spin. So instead of coarse graining, we can do some other operation. We can even, if we are able to define, let's say, a faithful representation in terms of the hidden spin, we are even defining a dual description of the original system. So let's say that these frameworks adapt to different interpretation or operation depending on what we do in practice. In general, we want to consider less hidden spin than visible spin, and in some way we want to encode in some macroscopic hidden spin the dynamics of more microscopic degrees of freedom. Okay. We are defining a variational ansatz, and so an optimization problem over the parameters. And the objective of this optimization problem is formulated in terms of the free energy. So we want that the free energy of the visible and the hidden spin is as close as possible. Okay. Now, let's essentially repeat the same exercise, but now we are in the context of machine learning, in the sense that we consider networks that are called restricted Boltzmann machines. They are not immediately related to the neurons I showed you. So there are some, let's say, hidden comments that I am not making now. But take simply the idea, for the sake of this slide, that we have some networks that are ansatzes for probability distributions, and that they are ansatzes that work in this way, in the sense that they have an energy function, which is expressed as couplings among spins, that is put in the exponent here, so making a Boltzmann weight, and here we have the joint probability of visible and hidden spins. If we marginalize either on the visible or hidden, we obtain some parametric distribution function for the subset of indices. And here we are interested in a different objective. Okay, we tune the couplings such that the relative entropy, the Kullback-Leibler divergence between the true distribution and the parametric one, is minimized. So this, in words, means that the two distributions are similar. Okay, if they are the same, this divergence will be zero. So
what is the big P
the
there?
big P, sorry, I borrowed it from the, let's say,
Okay.
It's the original system that we want to discuss. So let's say is the true distribution. Okay.
What is lambda?
Lambda, yes. Lambda is a collective name for all the couplings that we have introduced.
So you're using, for some reason, the canonical distribution.
Yes.
So you're supposing you're at some thermal equilibrium.
Well, yes, I'm supposing that the probability distribution can be expressed in the Boltzmann waveform. Yes. Yes. Here, actually, I am not putting any temperature. Later, I will do, but I mean, there is a beta put to 1. Yes, in this form. So, essentially, we have repeated twice the same exercise. The function that we considered can be mapped pretty precisely. But the important point is that we consider two different problems, two different objectives. So we have two problems that are formally related. Let's say they can be implemented in the same neural network, so to say, but they have different purposes. In particular, and probably not surprisingly, the physical renormalization group asked just a global objective and a global comparison between the two distributions. While on the machine learning side, we are more demanding and we are asking something which is local. So it is a local comparison between the two distributions. So let's say the second requirement is more restrictive, and in some sense, it implies the first. Let's say that if we are able to minimize this one, we are also in a good position for the first. And this does not come as a surprise if we think a minute about that, because what we are interested in the physics side is to have a thermodynamic description of the system. So we are interested of taking a system and of integrating away as much information as we can, and just retain some global parameter that describe the system. So this is the interpretation of maintaining the free energy. Yes?
So can I understand this different as like thinking that every point in a space has a different Hamiltonian?
Maybe, I don't know, because as we were commenting, probably there is always some equilibrium assumption in describing this probability distribution. I don't know if splitting in many Hamiltonians has some issue in relation to that, but maybe, yeah. But anyway, let's say the point you are raising is true in the sense that here we are sensitive to something which is more local. So it is related to finer information, and it is not surprising that in a generic machine learning task we need to be more demanding. For example, if we want to take a classification problem distinguishing cats and dogs in images, no? It is easy to imagine that we need more than just one or two parameters like to distinguish between them. So the intuition is behind this stricter requirement is that. Okay, so the moral of this first block is that even in cases in which the connection at the formal level can be made precisely, which is not always the case, even that it is likely that the objective in the two realms of, let's say, physics and deep learning can be very different. And actually, an important comment is that here we are speaking of minimizing a relative entropy, but we are usually interested in doing that up to some extent, in the sense that if we are able to minimize the relative entropy perfectly, I think it's not possible. Okay, perfectly, it means that we are after one step we have a distribution which is identical to the original one, which has the same information. But the situation is usually that we want to lose information, lose irrelevant information, only to retain the relevant. And I'm using irrelevant, I mean, to provoke the suggestions that they do. Okay, so if there are no questions, I move on to the second block. The second block will be, oh no, there was a question maybe?
Yeah, can you go back? So
Yes.
I don't understand again. E sub lambda, what the small piece of lambda is?
Small p of lambda is, let's say, our ansatz. And lambdas, well, they were couplings, but they are parameters that we are optimizing over. And the P, the big P is the distribution that we want to represent, that we want to copy or to encode in some simpler description. Let's say P lambda would be hopefully a simpler description of what is relevant in capital P.
Daniel, can you give a broad idea of what are the variables in the case of machine learning? Because I'm not being able to understand like what the equivalent of the spins or the physical variables you are integrating out and all that are in the machine learning setup.
Right. In this setup, there are spins. Okay, so I'm applying that to a spin system. So otherwise, in the wide context, there is a variety of possibilities. When speaking about neurons, for example, applied to image classification, they are the pixels of an image. So they are real variables, or they can be very, very generic. Let's say I'm not committing to anything specific unless I need it for.
But should I think of this, if there were a neural network, should I think of this as a core training of the neuron?
You can imagine in a hierarchical sense. You can imagine that in a layer you are sensitive to combinations of neurons in the layer below. So it depends on the shape and on the topology of the architecture. But in general, for example, if you reduce the number of neurons, you have some sense in which you are doing a coarse graining.
Okay.
And I guess the second block will will further give some useful insight.
Daniele, so what is the memory here?
The memory is in the weights, in the coefficients that you are optimizing over. In this case, are W's. They were the lambdas of the statistical mechanics.
Okay, so that is the role of memory.
Yeah, let's say if you think to the neural network as a complex physical systems, the state of the system is the collection of the weights. And so you can think of training as an evolution of a dynamical system which change states and which evolves in the weight space. Okay. I guess it is not active. Oh, yes. So the second block, it is maybe less technical, but it should sound familiar in some aspects. Let's take an example. Take 15 neurons and arrange them in 3 layers. And here we have a cylindrical architecture. So we are not shrinking, let's say. We have 5 neurons for each layer. We don't want to connect the neurons of the same layer, but we do want to connect any neuron to all the neurons that lay in the layer below. And you might observe that already with just a few neurons, because 15 is a very small number, we have a pretty tangled architecture, a pretty complicated set of connections. So it seems like a good idea to try to simplify this, so to prune the network. And in order to do so, we can appeal to some a priori idea of, for example, of locality. And what I mean is that we can, for instance, say, okay, any neuron will be connected only to the neuron that sits right below it and to the neurons that are its neighbors. Meaning that, let's say, if the vertical axis is time, there is a finite propagation speed on the horizontal direction. So in doing so, it is not a mystery that we are building something which is a light cone structure. So in particular, if we take this neuron, it will be able to be causally responsible for things that happens in a cone within the network. Okay. But now that, I mean, maybe this sort of comment sounds familiar because we are thinking of light cones, but what we have obtained actually is the convolutional neural network architecture. So let's say with a reasoning on locality, we have obtained what is fair to say it is the main character in the deep learning revolution of the last decade. So this architecture is responsible for a big boost, for example, in image and speech recognition problems. And as we know, the light cone can be looked toward the future, like we were seeing from the input to the output, but also in the opposite direction. There is the past light cone. So we can think, for example, that a neuron in the second layer is influenced only by a cone of neurons. And this is what is called in deep learning the receptive field. So this neuron has a receptive field, which is constituted by these three.
Daniele, did you mean that these convolutional networks are more efficient for image recognition or speech recognition than the generic one?
Yes, that's correct.
And is that somehow related to this idea that you mentioned before, that forgetting part of information is better for the network for deep learning?
Yeah, partially. Let me comment. I will come back to this question in one slide. Okay.
Okay.
So the extra ingredient, which I'm lacking to answer this question, is symmetry. So it's translational symmetry. Okay, and part of the success of convolutional network is due to that. With translational symmetry, better translational covariance of the network, we mean that links which are functionally the same, let's say vertical links between the first and the second layer, have all the same weight. So any link was morally related to a coefficient that is tunable. If we want the network to be symmetric, it means that we are taking, as the color coding is suggesting, a specific class of networks. So we are reducing a lot the number of possibilities. And if we combine the idea of a receptive field with, let's say, with compact support and translational covariance, we are, well, this is possible to see in the formula, we are actually building the convolution operation. So we have a kernel and we are sweeping the kernel through the horizontal axis, doing what is technically a convolution. So
the notion of locality is something that should be sort of inserted from the structure of the data. So I understand that you want to see image, so there's a notion of locality of pixels.
Yes.
But if the data are features, there is features. Where is it coming from?
Yeah, this is true. I answer to this and to Jose's question at the same time, if I can. You're right. There is some locality is a property of the images or the sounds of speech that we are analyzing. It is not a generic property of any possible problem. But it proves to be a good a priori bias in these sort of problems. Let's say, for example, image classification. I mean, you take images, you understand the locality is important. And actually, to answer to Jose, the point is that, of course, the more complicated network contains the simpler one. So this is more expressive, and this, if well trained, can obtain the same result of the simpler one. The point is that it complicates the treatment too much, and this complication prevents you to reach so good a result. Meaning, for example, that if you have understood that you have a symmetry in your problem, it's better to go to a covariant formalism. Of course, you can work with explicit formalism in a basis or taking into account all the bases together, let's say. But if you recognize the symmetry, it's better to implement it a priori. And this is the idea of moving from a fully connected general network to one that already a priori embeds some knowledge of the problem you are solving. So in images, you are embedding in the networks the knowledge that locality is important. Okay. And this is true that images are, of course, images of physical things. So it is probably natural to expect locality. But sometimes it is also true that the physical intuition is a useful guidance even beyond its natural applicability. Let's say, if you have some idea about symmetry that worked in a physical context, even if, well, it's a good idea in general to try to export it beyond, in the sense that you have some mechanism or some bias that prove to be sound, at least in a context. So in a convolutional case, for example, you have many convolutional layers. So the first one will look at the physical image. But if you go deeper in the network, the fifth is looking to an image of features. So to expect locality at the level is not that straightforward. But still, experimentally, at least, it works. Let's say these networks are very deep, and this convolutional idea, well, entails a lot of layers. So it works also deep down the network. And it's fair to say that the last part of the networks, for example, for classification tasks, the convolutional neural networks are fully connected. So in the end, the classification task is done by a fully connected network. So you can think of the convolution like a filter that feds another network. So this was the end of the second block. I don't know, how am I doing with time? Yeah.
You have 20 minutes.
Okay, perfect. And well, let me stress and underline that this point was that I made in the second block was rather qualitative at this level, but it is suggestive because we are relating the structure of a network to a light cone structure. So it is at least suggestive and worth exploring that if we have deep learning, which is somehow related to renormalization, and the networks that are related to a space-time structure, is, of course, it is suggestive also in the sense of development like holography, where the geometry, a space-time geometry, is effective in analyzing a renormalization problem. Okay, I'm very qualitative in saying that. It is just a hopeful comment, let's say, that there are interesting things to be seen. And let's say the hopeful point is that a simple reasoning about locality, it is already providing us with, let's say, a physical justification of why some successful network is working with a good performance. Okay, so now the third is maybe a slightly more technical because we are trying to go to the front of the research. And we are looking to the training dynamics of the network. So as commented before, we think to the neural network as a physical system, which moves in a very multidimensional space. The weights are the parameters which describe the state of the networks, and the training is a dynamic in this space, which goes towards some desired configuration. So I guess that more or less this is what I have just said. So the training dynamics is a path in a loss landscape. Loss function, I will use maybe loss and energy or potential in an interchangeable way, because we have a cost, or cost, also another way of saying the same, we have a cost function that we want to minimize. So the training is the search for a path in this landscape that is looking for possibly global minima or minima that have some desirable characteristics. Of course, the thought goes to out of equilibrium systems or driven system. In this case, we have a network which is driven by the training data that we are feeding. Needless to say, is a complicated system. We have a lot of neurons, so it's a complex system. And we describe it as a stochastic process, as I will show in the next slide. So we are in the realm of the analysis of Brownian motion of complicated systems, and we can use some of the standard technology. It is interesting, for example, to consider Fokker-Planck equation to account for some characteristics of the training dynamics. And let me just make 2 comments here. Well, Fokker-Planck is essentially a continuity equation for the probability. So let's say it has a very physical interpretation. And in the context of training neural networks, it is relevant because it helps to condense some complicated training dynamics, at least approximately, into few characteristics. For example, like a temperature or a cooling down of a system. When you have this description, you can see, for instance, how different parameters of your networks relate to a common temperature. And this is useful because maybe you discover that different configurations of your parameters are in the end equivalent. So if you want to find the best configuration, you can, you can simplify your task from the beginning. It is called, this problem in a technical term is like a search in the hyperparameter space of neural networks. And the minimization algorithm, so the recipe that we are following to find an optimal configuration, is called stochastic gradient descent. And its dynamic is the Brownian motion that I was mentioning. So, sorry, here I'm using different symbols. X are the variables that describe the state of the system, the position of the system. So these correspond to the capital W's in previous slides. Okay, and the discrete time evolution of the system is that its position is at time k plus 1 is equal to the previous position plus a velocity times a parameter which is called learning rate. It is like the measure of the interval time. The velocity is given by the velocity at the previous step with an inertial coefficient, which is called momentum, also in machine learning. And there is the driving force, which is the gradient of the cost function, well, minus the gradient of the cost function. Note that the cost function f here has a gamma, meaning that this is an empirical cost function. So let me make an example. Suppose that we are doing the training of a neural network for classification of images. We have a lot of images, and we want to do the single training step without using all the images that we have. We just sample a subset of the whole data set, and we compute the step on this empirical cost function. We are doing that essentially because we have limited resources, and we are doing, and so we are more, instead of doing gradient descent, which is something that we cannot afford, we are doing stochastic gradient descent. This, which seems like a way of coping with a limitation, it's actually a very, very good idea for the dynamics of the optimization, in the sense that if you have experience with annealing problems, for example, so minimization problems, you probably know that if you add a temperature, if you add some noise to the optimization problem, you can easily improve its success. One such case is, for example, that with some noise, with some temperature, you can avoid being trapped into relative minima, and you can jump and find possibly better. And here, the empirical function can be written as the true loss function plus a noise term, and this noise term is, let's say, the noise driving, which can be described as a Wiener process, so Brownian motion. Okay, I'm not entering in more detail here, but okay, this noise is a very important feature, and actually we have transformed the limit in a resource. So the fact that we have limited time or memory resources made us, well, smarter in some sense, in the sense we have a technique which is more efficient in minimizing. And let's try to understand some aspects of the good effect of noise. I think this is a sketch of a loss landscape. Of course, it is very sketchy in the sense that the horizontal axis is supposed to represent the multi-dimensional weight space, and the vertical axis is what the cost is the loss. We can have different minima, maybe a very low but sharp one, or a wide valley, so a large one, which is a relative minimum. It is a fact that the stochastic gradient descent algorithm contains a bias towards going to this sort of minimum, so towards wide valleys, okay? And let's say that the stochastic gradient descent finds efficiently and almost systematically these sort of configurations that, sorry for jumping back and forth, you see, you can describe them as a cluster of configuration sharing more or less the same cost. Okay, so stochastic gradient descent has somehow embedded in it intrinsically a bias toward finding configurations which are in good company, okay, which are in company of other configurations that are similarly good. And from an intuitive point of view, you can understand that probably having a wide valley is a desirable feature, because it means that we are essentially insensitive to many parameters. So if we are in a wide valley, we have somehow forgot about many details which are irrelevant to the purpose of getting a lower cost. So it is a useful bias in practice. And in order to try to understand why the stochastic gradient descent through noise is able to implement this bias and to possibly enhance it, is a good idea to redefine or to modify the cost function in such a way that we put an incentive towards going to wide valleys. Let's say we want to put an incentive which drives our system towards regions that are toward the clusters, towards solutions that are in good company. So probably, in speaking about some counting functional, it is not surprising to find out that what we need is an entropic function. The intuitive idea is that we have the loss landscape that we had before already, and we want to smoothen it. So we want to have some representation of that which is less detailed. You can think, for example, to a local average, and you see, if we consider a local average over a scale which is now, it is expressed as gamma to minus 1/2, let's say, but there is, let's say, a dimension, a scale that you are putting by hand, and you are averaging over this scale, you can erase the sharp minima by averaging, while you leave quite unaffected the wide range. Okay. So this is the idea we are following, some smoothing technique, and in the wide range of possibilities, we are taking inspiration from statistical mechanics. And let me comment this entropy function here. It is very similar to a free energy. You can recognize it. But there is an important difference. It is a local function, a local functional. So in contrast to thermodynamic potential, it has a dependence on the spot. And this F will be our new loss function. But I will comment its details. You see, here there is the loss function L, which is the energy. Here there is explicitly the inverse temperature, beta. And so we are building a Boltzmann weight here. And there is an interesting term here, which is a shift in the exponent, which is related to a distance function between one point and another on which we are integrating over. So you can see that here we are making a convolution of the Boltzmann weight with a Gaussian kernel. Okay. And the gamma that you were seeing is this parameter related to the width of the kernel. Okay. Well, we can also, as a limiting case, consider sending the temperature to infinity, and in this particular situation, we have actually what we are providing is the continuum version of a weighted counting of configuration. Essentially, we are computing a volume. Okay, this I make a small detour. Tell me if I am short of time, that I will. 5 minutes, perfect. So I can do this detour just to enrich the intuition. You can think that we need to integrate away some information, some detailed information. So this is translating into a filtering operation. And we can think that the filtering operation is implemented through a convolution with a kernel, which is now generic. Okay. Let's see two extreme cases of this operation. One is when the kernel is trivial, so just a constant. In doing so, we are defining the partition function. So we are going, let's say, toward thermodynamics, which we have sort of already convinced ourselves was the most radical kind of compression that we can have. On the opposite side of the spectrum, we can have the kernel being a delta function, in which case the convolution operation will be just the identity. So meaning that in that case, we are not throwing away any information. We are just faithfully return the original function. So you can think of these local entropy as somehow intuitively in between these two extreme cases. Okay, so the fact that it is called entropy is obvious, and probably also the fact that it is called local because there is a dependence on the spot. Okay, so I don't have time to enter into the details, but let me simply state that the gamma parameters, so the characteristic of the kernel, can be less rigid than what we saw. There can be anisotropy in the weight space, so we can have different width of the kernel depending on the direction. And also there can be a non-trivial dynamic in time of that coefficient. It can be tuned from outside, like a driving, or it can be adaptive. So there can be some, yes.
By time, you mean the training time?
Sorry?
Time is meaning what there?
The training time.
Well, what do you mean by time?
Time, yes. Let's say the training was described in terms of a dynamic, discrete time dynamic evolution. So there are discrete steps.
Okay.
So time is the number of would be the number of steps.
So how do you prove this with that F, with that local entropy? You change this rule?
What do you mean by this?
I mean, the W's are these X's, no?
Right, yes.
Now you have that local entropy. What does it mean at the level of this?
Okay.
This dynamics?
Yes, the local entropy means that we had an original loss function. We traded it for a new loss function. So we are defining another problem with a different energy. The new energy, the new loss function will be this one. And we train the neural networks using F as the old L. So it means that the qualitative description, the new problem is still of this time, but the F that we are using is another loss function, which is implementing the entropic bias. Okay, this is, let's say, generic. I'm not here committing on the specific.
You say loss function or cost function?
Well, I'm using maybe interchangeably, yes.
The same thing?
Yes, in the sense that the loss function is the quantitative expression of a cost that you want to minimize. Yeah. And okay, so there is no time to enter into the detail, but let me just mention that these sort of arguments are not only interesting and appealing because they allow some intuition in terms of physical object that we know already, but they are also useful in practice. Okay, and they can be of general relevance. So let me conclude, and okay, maybe I'm not able to comment the detail of some things that are here, but what I want to stress is the general message that tools that we develop in physics and specifically in renormalization can have a hope of being promising on a practical level in the realm of deep learning. And even if not so, it's a good starting point to gain intuition, because as you probably know, neural networks work better than we understand them. In some sense, there are some surprisingly good performance, which it is not satisfactorily explained, which we don't understand. So I guess that the tools that we are familiar with have a good chance of playing a significant role. They already did, but also in the future. So, okay, thank you very much.
Thank you.